Hello friends, to continue with our discussion on severe plastic deformation, this last lecture of this particular module, I am presenting a case study, and I am using friction stir processing again as the technique for this particular case study, and we are looking at the one of the deformation method, or the one of the deformation process, which is called superplasticity. I have mentioned this particular word couple of times during previous lectures. So, I will introduce you what do we mean by superplasticity. So, basically superplasticity, if you want to define, it is the capability of very fine grained polycrystalline material. So, one of the requirement is that you should have very fine grained materials. Polycrystalline, already we have polycrystalline material usually in all engineering applications, and they undergo very high tensile plastic deformation. So, if you see the sample which was initially of this size, after deformation it has shown the deformation of around 1000% here. So, very high elongation, 1000% means in normal engineering alloys high ductility means 30-40%. If some alloy is showing 30-40% elongation, that is considered as very good ductility. Whereas, in this particular condition you can see the elongation is around 1000%. So, and the other unique thing which you can see here is that the deformation is uniform throughout the gauge length. So, it is a one single dimension you can see from very close to the shoulder to the other part of the shoulder, the deformation is uniform. There is no deformation localization, there is no neck formation. So, this kind of elongation, very uniform elongation you are able to get. So, in this case, in this particular materials you can get very high elongation. And in superplastic region, of course, stress is a strong function of strain rate, and that is what we call as strain rate sensitivity. So, couple of graphs are shown here, that when you plot ln of strain rate versus ln of sigma, in superplastic window, you see that the slope is quite high, where material shows superplasticity, and then m start decreasing. That is where in this particular material we say power law breakdown is there, and in lower strain rates you will start going towards the creep kind of deformation. So, there is a strain rate window in which the strain rate sensitivity is very high. So, if you see the m as a function of ln of strain rate, so m has been calculated from the slope of the top graph. So, you see that the m is very high where the superplasticity is expected, and m is usually more than 0.4. What is the effect of m? Already we have seen that when m of the material or strain rate sensitivity of the material increases, your elongation is increasing. So, for example, m of 0.6 is able to give you a elongation of around 1000%, and these are true for different set of materials. For example, here titanium and zircon are plotted, and when m is lower than 0.4 or around 0.3, you cannot even reach maybe around 100% or so. And as you go towards m of 0.1, let us say the elongation is around 50%. So, the elongation is a strong function of strain rate sensitivity. The application of superplasticity is of course superplastic forming. The idea is that when you have superplastic deformation, these are all high temperature deformation, the flow stresses are very low. So, you can deform a material just by using gas pressure. So, all these parts which you are seeing here, these part they are formed, these are metallic part, but formed only using gas pressure, which we do generally in case of glass blowing operation or making some plastic part. Okay, that is these products are made by just applying a gas pressure. Okay, and whatever the die shape is there, the material take that shape. Okay, so this is what as one component is taken out from a furnace. So you keep it in furnace, apply the gas pressure, and whatever is the die shape on the other side, you can get the shape of that die. So you can form very complex shapes, as you can see one shape here. Okay, very complex shape. Okay, very complex geometry, and this can be made only in one go, means only one cycle you can produce the whole thing. If you are going to do with this with conventional fabrication method, all these parts will have to be made separately, and then they will be joined using welding or some riveting techniques. Okay. So, in one shot you can get a very complex shape like this in superplastic through superplastic forming. Okay. So, as I was telling you that, for example, this is your initial sheet which is shown by orange color. Okay. Then you have applied the gas pressure and the shape of the die is shown here. Okay. So, when we are applying the gas pressure, the sheet is deforming. So, this red one is the deformed sheet after forming. Okay, and it is able to take the shape of the die by applying a constant pressure. Okay. The other very good advantage of superplasticity and superplastic forming is that you can deform or you can form these complex geometries in materials like titanium and magnesium, okay, which are hard to deform, okay, because they have hexagonal closed spec structure, HCP structure. Okay. So, they have very limited slip system. So, deformation at room temperature through dislocation movement is very difficult, okay, and they generally have very low ductility. Okay. But with this technique, because here the deformation is not through dislocation movement, the deformation is through grain boundary sliding, which is what we call as GBS. Okay. So, the crystal structure is not a factor here, okay, because deformation will be on the grain boundary. So, you can easily form material of titanium and magnesium alloys also through this process, and the advantage of doing that with titanium and magnesium is that they have low density. Okay. So, these are lightweight. So, very important for aerospace application. Okay. So, this is what already we have discussed about the strain rate sensitivity. Okay. Now, what is the effect of what are the general requirements for a material to show superplasticity? Okay. There are three main conditions, for example, that the microstructure should be equiaxed, okay, have equiaxed grain morphology. That means, in any direction if you measure the grain size, it will have same size, okay, and the grain size in conventional superplasticity should be less than 10 micron, okay, around 10 micron, it can be 15 micron also, but the limiting condition is around 10 micron, okay, because when you have fine grain material, then only you have more grain boundaries, okay, and then the deformation happens through grain boundary sliding, okay, as already I told you. So, all these equiaxed grains, finer grain size helps in the grain boundary sliding process. Okay. The deformation condition, the temperature has to be above 0.4 or 0.5 TM. Okay. So, this is where you have high temperature deformation conditions, okay, and the strain rate is around 10 to the power minus 3 per second. Okay. So, strain rates are very low as compared to other forming processes or hot deformation processes. So, that is the only drawback of superplastic deformation. Okay. One is of course high temperature, that you have to take material to high temperature, and the other is the very slow strain rate. So, when we are doing forming also, one part will be produced in a very long time. Okay. So, the productivity will be low if you have a superplastic, if you are going for superplastic forming. And of course, strain rate sensitivity, as already told, should be more than 0.4. Okay. And what is the effect of grain size? If you see the grain size, how it affects the strain rate sensitivity M. Okay. So, these are strain rate values, this 10 to the power minus 4, this 10 to the power minus 3 and so on, okay. And the m values are 0.1 here, okay, 0.2 here and so on, okay. And the grain size is increasing in this direction. So, the effect of grain size is that as grain size is decreasing, okay, for example, okay, they have shown in inch, you do not have to worry. So, grain size is decreasing in this direction, and you can see that what is the effect of decrease in grain size on strain rate sensitivity. So, as grain size is decreasing, the strain rate sensitivity of the material is increasing, and of course, you have to look for the superplastic window here, which is around 10 to the power minus 3 here, okay. So, above that only you have strain rate sensitivity of more than 0.4, okay. So, in this window, and as the grain size is reducing, my m is increasing, okay. And you can also see that as m is as grain size is reducing, my window for high strain rate sensitivity is going towards higher strain rates, okay. So, for example, in a very fine grain material, I can have superplastic window extended up to 2 into 10 to power minus 3, okay. So, if you can reduce grain size further, you can still go to higher strain rates. So, the effect of grain size is very strong, that by reduction of grain size the m increases, and also the window for high strain rate sensitivity shifts towards the high strain rate, okay. That means, I can deform at a higher strain rate, that means the time for deformation will be smaller now, okay. Now, for getting superplastic deformation or material for which can exhibit superplasticity, okay, usual method is of course your normal thermo-mechanical processing to have recrystallization in the material to generate fine grains fine grain size material, okay. So, normal thermo-mechanical processing like rolling, extrusion and all these processes are already there, okay. So, precipitation will be done, and precipitation is simulated nucleation of grains, new finer recrystallized grains will be there. All those complex thermo-mechanical processes are there for production of material suitable for superplasticity. The problem with those methods is you have to have very intimate knowledge about materials to get material suitable for superplasticity, okay. In this friction stir processing is a very promising technique, okay, which has been able to generate this fine grain size material in one cycle. So, just by traversing the tool through the material, you are able to generate the fine grain size material in one shot, okay. So, I do not have to do a very complex thermo-mechanical process to get the fine grain size material. And the microstructure which is there in the nugget zone or the stir zone, okay, fine grain size material, fine grain size microstructure, that is able to satisfy the condition required for superplasticity, okay. Already whatever requirement in that we have seen. So, the microstructure which is in the stir zone or nugget zone is the one which is able to satisfy those conditions, okay. Now, the problem with FSP is that which we have already seen, that you have a microstructural gradient. So, only the microstructure will be refined depending upon the the length of the pin, okay. So, if my pin is up to here, the refinement will takes place up to here, okay. Recrystallized grains will be there, and above that it will be a thermo-mechanically affected zone, means it is elongated grains, not recovered grains, okay, which is not suitable for superplasticity. So, this material is suitable for superplastic deformation as defined in our previous slide, whereas this material and above this coarse grain also, this you can say is non superplastic, they cannot exhibit superplasticity, okay. So, now the idea here is that to understand this deformation behavior of these fine grain, coarse grain material separately, and then what is the effect of this combined microstructure on the superplastic deformation. Okay. So, one should understand that is when only we will be able to use FSP as a technique for microstructural or for superplasticity. Okay. So, the idea is to understand individual deformation behavior of fine grained material, coarse grained material, and the combination of this, which we will be calling as composite material, composite microstructure. Okay, before going to that, okay, we have discussed about multipass, that I can use multipass FSP to get a bulk microstructure, okay, or I can use it as a bulk processing. Okay. So, in that it will be a interesting thing to understand that what will be the effect of multiple processing on the material which is already processed. For example, if we are starting from here, this is my first pass and this is my last pass. Okay. So, what will be the effect of this first pass on the material which is still unprocessed? That means, I will call it as preheating. Or what is the effect of last pass on the first pass? Okay. Then that means, it will be a post heated material, post heating. Okay. So, what will be the effect of this individual passes on the microstructure of the material, whether microstructure is changing or the properties are changing. Okay. To do that, first we measure the temperature, okay, that what is the temperature rise when you are doing FSP. Okay. So, suppose the pass has started from here, okay, and going in this direction. So, a thermocouple placed here measures the temperature. Okay. So, the temperature goes up to around 250 degrees Celsius. Of course, we are measuring the temperature away from the stir zone. Okay. I cannot measure in the stir zone. So, there it is around 250 degrees Celsius, and then quickly coming down to room temperature in around 200 seconds. The next thermocouple measures the temperature which is placed somewhere here, okay, temperature rise of 300 degrees Celsius, and then coming down also again in a very short time. What is the effect of this when the processing is being done here? What is the effect of that in the already processed material? That is shown with these two curves here. Okay. That says that the temperature rise in the other part of the material is not very high, it is even lower than the 100 degrees Celsius. Okay. So, effect of the first pass on the other part of the material is very small. Similarly, when you see the last pass, okay, the temperature rise in the thermocouple which are placed here, it is around 300 and 400 degrees Celsius. Okay. But the temperature rise in the thermocouple which are placed here, okay, is very small, only up to less than even 100 degrees Celsius. Okay. So, we can conclude that there is not much effect of individual passes on the microstructure of the it should not be too much effect on the microstructure, because the temperature rise or the temperature comes down to room temperature at a very short time, okay, within 200 seconds or so, means it is only a exposure of 3 or 4 minutes, and there is not much effect of temperature on the other part of the sample. To confirm it more, what we did is we took sample of a large process material from different locations, okay, and these are the deformed samples, okay, specimen 1, 2, 3, 4, 5, 6, and you can see in all the cases the deformation is very similar. Okay. There is not much effect of the thermal cycle on the microstructure as well as property of the material. Okay. So, now taking material sample from different part of the microstructure. So, this is a fine grain microstructure sample for that, this is for coarse grain, okay, and this is for the composite one. So, in the coarse grain one, you can see that there is a large reduction in the cross sectional area, that means there is a flow localization here, whereas in fine grain one and the composite one, more or less the deformation is uniform. Of course, we have gone up to failure, that is why you see necking in the last part of the deformation, but more or less the deformation is quite uniform, okay, and the effect of that you can see on the elongations also. So, at different strain rate deformations were done, Okay. The interesting part here is that the fine grain, which is shown by this square box, okay, is showing maximum elongation of around 350%, whereas the composite microstructure which contains both the fine and coarse grain, which is shown by this upright triangle, okay, the elongation is shown around 450% or so. Okay. That means the material which has both fine and coarse grains are showing higher ductility, higher elongation. Okay. So, somehow it looks like that the fine grain which is there in the nugget zone or stir zone is helping this coarse grain microstructure, and in the process you are having continuous dynamic recrystallization. Okay. And this addition of fine grain in the material is helping the composite microstructure to show higher elongation. Okay. So, to confirm this what we are proposing, okay, we did microstructural analysis. So, this is the initial fine grain microstructure, okay, only when we have taken the fine grain microstructure. Okay. After deformation it is showing dynamic grain growth. Okay. So, the grain size is increasing, as you can see, this is the initial grain size, this is the final grain size. So, from 5.7 we have come to 13 micron during the deformation. If you see the coarse grain part of the FSB material, okay, after deformation also it remains coarse. Okay. There is no dynamic recrystallization is happening. Okay. Coarse microstructure remains coarse, so grain size is 40 micron and still it is 40 micron in the after deformation. So, there is not much change in the microstructure, okay, and of course, ductility is also very low. Whereas, if you see the composite microstructure, this is the gradient you can see in the microstructure, fine grain, coarse grain. Okay. So, this is my fine grain, this is my coarse grain material. Okay. And after deformation, if you see the microstructure is now uniform throughout the cross section. Okay. So, this coarse grain microstructure has undergone dynamic recrystallization, which is what we call as continuous dynamic recrystallization, and refinement is taking place, whereas in a single coarse grain material or uniform coarse grain material you do not see any CDRX. Okay. So, these fine grains are somehow helping this coarse grain to undergo CDRX process, and you can see effect on grain size also. It is from 29 micron it is going to 16.7 micron. The very important effect of this microstructural change you can see on the strain rate sensitivity. Okay. So, if you plot strain rate sensitivity as a function of true strain, okay, that means after different deformation stages, what is the strain rate sensitivity? The strain rate sensitivity of the fine grain, this is my fine grain layer, okay, though it is initially very high, more than 0.4, but it is continuously coming down with the deformation process, and that is due to coarsening of the microstructure. As we saw for fine grain material or fine grain size material, the M was higher. For coarse grain, M was coming down, we saw one graph like that. So, because of this dynamic grain growth which is taking place, my M is continuously reducing. In the coarse grain material, of course, the M was low from the beginning and it remains low throughout the deformation process. There is no change in the microstructure. Whereas, in composite, if you see, okay, the strain rate sensitivities remain continuously high, more than 0.4. Okay. And the reason for this continuously high M is because you are continuously having, you are feeding the material with fine grain size microstructure or fine, you are continuously refining the microstructure through CDRX process, and that is what is helping for M to remain high during the whole deformation process. Okay. So, this is what is helping to achieve higher ductility in the composite microstructure. Okay. So, to conclude, friction stir processing is an effective and flexible process to refine microstructure which can exhibit superplasticity. Okay. And you can achieve very good superplastic properties at relatively higher strain rates by introducing this inhomogeneous structure, a composite structure, and you can easily adopt FSP as a bulk processing technique by doing multiple passes. Okay. So, this is one case study on frictional stir processing using severe plastic deformation method, which is this FSP, okay, and where you can get superplasticity in the material. Okay. Thank you.